Okay, good afternoon, guys. I like the Phineas and Ferb, that's cute. Welcome to Friday, the end of our second week of Calculus 1. You guys are hanging in there. I'm really grateful to see everybody here, and we still got some people coming in, so I'm gonna get started kind of slowly with some announcements. First few things, turn on my screen share here. I am just now getting to some of the questions you guys have left me in WebAssign under the Ask Your Professor thing. I'm sorry if my responses there haven't been super duper quick. I do my best to clear all the extension requests every single day, but typing out those responses takes a little bit longer, so I don't clear them every single day. But I will do my best to stay on top of them. If you've been waiting for an answer there, I'm sorry. There are, I think, 3 more for me to get to before I'm done with your classes. Questions that came in that way. If you ever find yourself waiting longer than you want to, if you feel like you need a response to that question, it's driving you nuts, I want to remind you that there are tutoring options available. So if you go to, here we go, if you go to our course in Canvas, which is here, and you follow this link to the Learning Commons tutoring section, I'll open it in a new tab. Just double check that everything is still working as it should. You should be able to come down here to STEM tutoring. Here we go, Northwest Campus Math and Statistics. Visit the Learning Commons page. It looks like they have changed this a little bit, but it says for tutoring assistance in math and stats, go here. And then if you come down, I know it says STEM. STEM, remember, stands for science, technology, engineering, and mathematics. So if you want a tutor to talk to you like right now about a problem, you don't want to wait for me to reply to your Ask My Professor thing in WebAssign, you can come here by following those links, then click this. And this will take you to Zoom meetings. So if you want some math tutoring, you click here, that would dump you into a Zoom waiting room, and then they'll pair you up with a tutor and you can get help right away.
Okay, I just got in here. Quick question. Is there any way you can sign up to be a tutor?
So if you want to tutor, that's a totally different thing. Contact me. Contact me. I can put you in contact with Larry Warren, or you can email Larry directly. He is the guy who we hired to manage the tutors at the Learning Commons. So if you're interested in tutoring at the Commons, that's the guy you would talk to. If you're interested in tutoring in the P Building lab, you would want to talk to, misspell his name here, so I'm Googling it. There he is, Jason. So if you are interested in a job as a tutor, the man you would contact is Jason Margolis, and that's if you want to tutor in the P Building, that's mostly 1033. And if you wanted to tutor in the Learning Commons, you would contact Larry Warren. So those are the 2 managers for the 2 main math tutoring spaces we have. But again, the reason I'm showing you this right now is in case you guys want access to tutors. So again, the sequence of links you click, go to our Canvas page, click here, come down to the Northwest Campus, Math and Statistics, click here, then come down here to STEM and Business Tutoring. So that's down here. And that will put you to a space where you get dumped into a waiting room for a tutor. If you need help right away, that would be my recommendation. If you want to speed up an answer from me, if you've submitted something on WebAssign that you want some feedback on and I'm not answering quickly, also don't hesitate to send me a Canvas message, just like poke me a little bit. I do get busy, I'm a human, I get distracted, so I don't resent that at all. If you want an answer faster than you are getting it from me, feel free to remind me that there's something there that you want an answer to. Okay, with that said, we do have some other announcement-y stuff, but these are all the sort of things that I would like to write down. It's washing up pretty badly here. That should be better. Okay, so this is MAC2311, section 4. It is a lecture. And today is the 4th of September. Other important announcement-y things, the WebAssign temporary or free trial is about to end. Cengage, who is the publisher that owns WebAssign, like all textbook publishers, is an evil corporation bent on taking money and publishing needless new editions every year. And when they sent me the email reminding me to remind you that the free trial is about to end, they weren't kind enough to let me know when. So the usual rule is 2 weeks, which would mean if you signed up on the first day of class, it would end Monday, Labor Day. They didn't give me a time, they didn't give me a date, so don't hold me to that. They just told me this shit about to end. What that means is if you've been using the temporary free trial access, you know, if you scroll down instead of inputting an access code and click the use temporary access thing, they're about to kick you out. So please sort out your WebAssign access code before getting kicked out. Like, do it today. If you're having trouble affording the access code, or the place you wanted to get it from like didn't have it, or the bookstore was out or something, they told you to wait and come back, start pushing on those people today. You can email me or Canvas message me if you're having trouble with the money. Every semester, the department does invest a certain amount of money in access codes that we can give to students who are in situations that warrant that. You know, maybe your financial aid got messed up because your EFC changed this year, or maybe your job changed and you make less money now than you used to, so your Pell Grants weren't what they should have been. Situations like that definitely exist, hardships exist, and if you are falling into a hardship here about this issue, reach out to me. Reach out to me and I'll do everything I can to help you. Sometimes I can lean on the Cengage people to extend the trial access. Sometimes, like I said, the department does have some codes that they can give out and I might be able to get you one of those. But whatever it is, you don't want to get kicked out. You're not going to be unenrolled from the course at Santa Fe, but if your free trial access to WebAssign expires, you will get kicked out of the WebAssign class. And that means you won't be able to work on the homework, all of those things. If you're using the ebook, you won't be able to access their ebook. So it's bad news. You don't want that. This is not the right time to be falling behind in the class. We're just starting to ramp up. The semester is starting to get more serious. So you want to stay on top of shit. You don't want to get kicked out. Please stay on top of that, right? Don't let that happen. Other things, announcement-y things. There's no class Monday. Monday is Labor Day. And if you haven't researched the origins of Labor Day, you certainly should. It's a cool holiday that was fought for and won by labor unions in the United States. Labor unions give people who work regular jobs like you and me some bargaining power against the people who pay us for our labor. And it was, before labor unions gained strength in this country, it was much harder to be a lower middle class individual. If you're not born very rich, life was hard and there wasn't shit you could really do about it. So Labor Day is an important holiday worthy of the same sort of respect we give Veterans Day and Memorial Day. I would recommend that you take some time to research it. As a consequence of this, homework 2 is due on Wednesday. Right, so the homeworks are normally due on Monday, but because of the holiday, I don't feel it's fair to have something be due on a day when we're not going to see each other. I know it's easy to forget. So homework 2 is due on Wednesday, but please don't slack on it, right? Try to get homework 2 done before Monday. That way you can enjoy your holiday. You can read all about Labor Day. It's a wonderful thing. What else is going on? I think that's all the big announcement-y stuff. Pretty sure. So then today I'd like to pick up where we left off last time. The access codes, last time I looked, it depends on where you buy them. right, first. So there's a question in chat, how much are the access codes? They're usually around $100, right? Around $100 to buy one semester's access. Cengage sells them directly, and I think when I looked, they are like $119 from Cengage Direct right now. The bookstore also has them, the Santa Fe bookstore, and they might sell them for a little bit less. Can anybody tell me what the bookstore is charging for the access codes this term? Anybody buy one from the bookstore?
145, I think.
145? Shit.
Yes.
Damn.
Expensive. That sucks. You might be able to find them cheaper on Amazon. Poke around, talk to people. There are subreddits. I'm sure you guys are all familiar with Reddit and various flavors of social media. Check around anywhere you can that people talk about these sort of things. Try the UFL and Santa Fe College subreddits. There might be links or hints or discussions there about how to get them cheaper. But the two normal options are through the Santa Fe bookstore or direct from Cengage. Sounds like both of those have gone up. And I think Cengage is in the 120 range right now. And if the bookstore is charging 150, then they are. But ask around, ask people at the bookstore, and see what sort of deals you can find. Yeah, usually there's somewhere around $80. I think if I'm able to get it that day when I get the code, but gives me issues trying to get in the course. No, if you do get kicked out, the process to get back in, you just give them the code and they let you back in. The harm comes when like you get kicked out and you don't have the code yet and you got to wait for it. That's when you can end up losing a few days, and you really don't want that to happen. So again, my recommendation is don't let yourself get kicked out. If you think that's going to happen, like you don't have the code and you don't have the money for the code right now, email me, canvas message me. I'll work with the Cengage people to try and get your trial extended. I can work with you and the department to try and get you a code cheaper or something like that. But definitely communicate with me. Don't let it just happen and do nothing about it. Don't let it happen and just try to wait until your next paycheck. That will hurt you. And we can do better. We can find workarounds. So work with me, I'll work with you, we'll make it go. Any other questions about WebAssign access codes? Yeah. Let's see, what was that? Okay, cool, perfect. Let me see, I felt like there was something else I wanted to talk to you guys about. Did I not publish any of these yet? No, not for you guys, okay. No, then all right, then I think we are ready to just jump right back in. Last time we talked about continuity. And we had this important definition. This is section 2.5. Remember, we say the function f of x is continuous at x equals, I think I used a c, you can use a, you can use whatever you wanted here, at the number x equals a, if and only if the limit as x approaches a of f of x exists and is equal to the value of the function at a. Right, this is the main definition that we played with and explored last time. And then there's another kind of definition here. Sorry, that's def. I don't know what's going on with my pen today. The function f of x is continuous on the interval a, b, or more generally, on the set S, if it is continuous at every number in the interval or set. Right, so we like to say the function is continuous on the interval 0 to 1. That means for every single real number in the interval 0 to 1, and there's infinitely many such numbers, this definition, this first definition, is satisfied. You can't go through and check one at a time because shit, I mean, there's infinitely many of them. My hand would fall off, I would die long before I finish. So some theorems are useful. We had the following big theorems. Polynomial and rational functions are continuous everywhere in their domain. So for polynomials, that means they're continuous at all real numbers because every polynomial has domain all real numbers. For rational functions, that means they're continuous at all real numbers except the ones that make the bottom 0, because that's how you find the domain of a rational function. And then we had one more theorem, which said if f and g are continuous at x equals a, then so are f plus g, f minus g, f times g, f over g, and f of g.
Wouldn't f over g have some asymptotes, like sometimes? Wouldn't you consider it defined at like continuous at some points?
Well, so the catch here, remember, was as long as g of a is not 0.
Oh, okay.
Right. So anywhere these combinations are defined, they will be continuous as long as the two functions that you're building them out of are continuous. So this theorem says you can mash continuous functions together however you want. The result will be a new continuous function, as long as it's defined. This says nice functions are continuous almost everywhere, right? Polynomial and rational functions are continuous everywhere they're defined. And then these are the definitions that we need, specifically this one to get the homework done. Now, I want to take a quick look at your homework because today is the last day of the week and make sure that there aren't any specific skills or terms that I haven't introduced, but I think we've covered most all of what we need for this guy. So we could just practice solving problems, but let's make sure. So limit laws, sketching graphs, this is fun. Continuity questions like these, limit law questions like these. Yeah, in fact, we did look at all of these. So, is there anything else? We could poke ahead a little bit. We haven't really talked about limits at infinity, have we? So I think the homework ended at section 2.5, but this week I had intended for us to go a little bit further. So maybe what I'll do is this. I'll take any questions you guys have from the homework. There's no 2.6 stuff here, is there? No. And then I'm going to introduce the material from section 2.6, which I had intended to cover this week, or at least introduce this week. So we've discussed everything that you guys need to do the homework, which means you should be working on the homework. And that probably means we have some questions or homework problems that we've been having a hard time with. So what homework questions would you guys like to take a look at? Nala, Katie, no, that's not your food. Sorry, I got a greedy cat. Nala, no baby, not yours. Good kitty. Hey. No. Get out of there. Go. Go, go, go. Go. Can't steal your brother's food. Okay. (15) and 11, we can definitely take a look at. Okay. So we'll pull this over here. This is homework 2. Question 15. And I'm happy to be looking at this one because this limit is actually a limit we're going to need to define a derivative down the road. So this is the limit as h approaches 0 of x plus h cubed minus x cubed over h. And the question is just calculate the limit. Calculate the limit as h goes to 0. If I try to plug in h equals 0, the bottom is 0. So I can't calculate just by plugging in. In other words, this function, if you think of it as a function of h, think of the variable as being h, it's not continuous at h equals 0. So if we want to figure out this limit, we're going to have to use some of those algebra tricks that we talked about earlier. I would come off to the side here and calculate x plus h cubed. There's a fast way to do this. I don't know if you guys know it, using what's called Pascal's triangle. Yeah, the binomial theorem, right? So you can write out Pascal's triangle down to the n equals 3 row, and that will tell you right away this has to be 1 times x cubed plus 3 times x squared h. Here, let me do it. I'll do it down here.
And just referring to that, we're gonna actually use that to like prove the power rule, right? Like later on.
We'll use the binomial theorem, yeah.
Okay.
So what these do is they give you the coefficients of the terms in the expanded sum. This is x plus h all cubed. So you're going to have every possible combination of powers of x and h that add up to 3. So you've got x to the 3 and h to the 0, and that's your first term. He gets a 1. Then you'll have x squared h to the 1. That's your second term. He'll get a 3. Then you'll have 3x times h squared, and then 1 times h cubed. So these numbers, 1, 3, 3, 1, come from Pascal's triangle. If you don't remember the binomial theorem, though that's not the end of the world, you could also FOIL it out. It just takes longer. I'll leave this one alone and go ahead and FOIL these two. So this will be x plus h times. When I FOIL these, I'll get x squared plus hx plus xh. That's plus 2xh plus h squared. And then if I distribute this guy over that, I'll distribute the x first. So I'll have x times x squared, that's x cubed. And then x times 2xh, that's plus 2x squared h. And then you have x times h squared. And then I'll add to that what I get when I distribute the h times x squared, plus h times 2xh is 2xh squared. And then h times h squared is h cubed. And if you combine your like terms, you'll have one copy of x cubed. I have 2x squared h plus hx squared. Well, x squared h and x squared times h and h times x squared are the same thing. So this guy and this guy are like terms. You can add them up. You have 3 of them all together. You've got 2 of them here and 1 of them here, so that's 3x squared h. And similarly, you can add this guy to this guy, xh squared, xh squared. You've got 1 of them here, 2 of them there, so there's 3 of those. And then you got your h cubed. So however you get there, this is x plus h all cubed. You can't just say it's x cubed plus h cubed. That shit doesn't work, right? You got to FOIL. Fast way to FOIL is using the binomial theorem. The longer way is the longer way. This will always work. It just takes time. If you want to practice with the binomial theorem, you want a reminder how this shit goes, come see me in office hours. I'll be happy to share with you the full theorem. In any case, what we get here is the limit as h goes to 0 of this, which is this, minus x cubed. And all of this is being divided by h. There's some cancellation here, of course, the x cubed here and here. So what we're left with is the limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed over h. And now, remember our goal is to cancel the h from the bottom, so I need to factor. You step right before canceling always needs to be factoring. You can cancel if and only if you can factor. So let's go ahead and factor. This is lim h to 0. Upstairs, every term here does have an h, so I can factor an h out. And what'll be left is 3x squared plus 3xh plus h squared. All of this being divided by h still, and now we can cancel. So this is equal to the limit as h goes to 0 of 3x squared plus 3xh plus h squared. But of course, as h goes to 0, now that the h is gone from the denominator, I can plug in. This guy will be 0, it'll be 3 times x times 0. And this guy will be 0 squared, which is also 0. So I just get 3x squared. And it turns out this is what's called the derivative of the function x cubed. You might recognize this as being the difference quotient. You remember that object from pre-calc, the difference quotient that you would get for the function x cubed. And so the remark that Alex made there about using this to prove the power rule, yes, we will do that later. Questions on this guy? What we did, why we did it, how we did it? Everybody feels pretty good?
Yes.
Okay. So then I think going in order, the next one that we wanted to look at, this was 15, so we're necessarily out of order. I'll come back to 2 and then up to 11. Two is fun. I don't want to do every part of 2. I'd like to leave some of this to you, but I will take a look at some of them. And I'll leave the screen just like it is here, so you can see the graphs and you can see what I'm writing. We particularly want to see part F. Okay, so let me do parts A, D, I'll do parts A, E, and F. So part A, just to get us familiar with what we're doing, they want the limit as x goes to 2 of f of x plus g of x. First, we use our limit laws. We know that this is the limit of f plus the limit of g. Because that's what our limit laws say. It says the limit of a sum is equal to the sum of the limits. Now I look on the graph of f to try and find the limit as x approaches 2 of f of x, to try and find this part. Well, here's the graph of f. I imagine I'm a little guy walking along the graph, I'm stuck to the graph, and I want to get my x coordinate closer and closer and closer to 2. Well, here's x equals 1, here's the x-axis, so x equals 2, that's here. So if I'm walking along this graph like this, my y values are getting closer and closer to the y value of this whole. Right? If I'm walking along the graph, then my y values are getting closer and closer to -1. And that happens whether I'm coming in from the left like that or coming in from the right like this. So both of the one-sided limits as x approaches 2 on the graph of f of x, those y values, those are tending to -1. So this first piece here is -1. And then we'll look on the graph of g to figure out what he does near 2. Again, I imagine I'm stuck to the graph, I'm walking along it, and I'm getting closer and closer to having an x coordinate of 2. If I approach from the left, I'm going up to here, which looks like it has a y value of 2. And if I approach from the right, getting closer and closer to having x coordinate 2, my y value is also getting closer and closer to 2. So the limit of g does exist, and it's 2. And then -1 plus 2, that's 1. Okay, so that's the purpose of this problem, is to get practice with these limit laws. Let's look at part E. That's the limit as x approaches 2 of x squared times f of x. Well, again, using our limit laws, I can take the limit of each piece separately. This is the limit as x approaches 2 of x squared times the limit as x approaches 2 of f of x. Remember those limit rules that we discussed at the very beginning of this week? Think of these as your two functions, like f and g, or g and f. The limit of g times f is the limit of g times the limit of f. It's just that here they've given me an explicit formula for one of them, and they've given me this abstract formula here, this abstract quantity here, represented by the graph for the other one. The first piece, the limit as x approaches 2 of x squared, we have this rule that says limit as x approaches c of x to the n is always c to the n. This is as long as n is, what do we say? As long as n is greater than 0 when c is equal to 0. So in other words, you can just plug in, right? If this is a polynomial or power function where the power is positive and c is non-zero, then you can just plug in. So this guy is just going to be 4. Or you could think about the graph of x squared and do it graphically like that. That works too. Either way, this first piece here, this is 4. As x approaches 2, x squared gets closer and closer to 4. What about the graph? What about the limit of f? Well, as we get closer and closer to 2, the y values along the graph of f, we just did this one. From both sides, the y values on the graph of f approach -1 as x approaches 2. I don't care that there's a hole there because I don't care what happens at 2. I just care what happens nearby. I care about the pattern.
How did you get 4 again?
2 squared.
Oh, okay, gotcha.
Yeah, I just plugged in. That's
Okay,
it.
got it. Thank you.
Because this is a polynomial, we can get the limit just by plugging in. And then the graph of f tells me that the second piece here has to be, just like we calculated in the first guy, has to be -1. So this is -4. And then the very last piece, here, piece f, wants the limit, wants f of -1 plus the limit as x approaches -1 of g of x. So we need to figure out what f of -1 is. Put this here. So f of -1, this first piece, how do I figure him out? Definitely I need to look at the graph of f. It's this guy. -1, that's right here. This x value is -1. So the point on the graph appears to be, oh wait, there's a hole there. So what is f of -1? If there was just this hole here and nothing else going on at x of -1, when x is -1, it would be correct to say f of -1 is undefined. But there is something else going on here. Yeah, we see it. Daniel and Becca get it. It's not undefined because they've defined f of -1 up here. So this hole is not telling me the value f of -1. It's telling me the limit as x approaches -1 of f of x, but that's not what they've asked for here. That's kind of the subtle point. So if you come all the way up here, this y value is f of -1. And yeah, that looks like 1, 2, 3. So this piece is 3. And then the limit as x approaches -1 of g of x, what is that? If I look on the graph of g, here's x equals -1. If I get closer and closer to -1 from the left or from the right, my y values are approaching, it looks like 2. So this would be 5. So real quick, a reminder, even if your function has a limit at some particular place, that doesn't mean that's the value of the function there. I'll call this A, I'll call this B. If this is the graph of f of x, then f of c here would be equal to b. But the limit as x approaches c of f of x would be a. So it's a little bit of a subtle thing. The value of the function comes from the exact point on the graph. And the exact point on the graph here above -1, it's not the hole, it's up here. Even though the limit as x approaches -1 is defined by the height of the hole, the actual value of the function there is defined by the dot, the filled in piece. And this tells me something specific about this function. What could I say, thinking in terms of what we talked about last time and at the start of class this time, about f of x at -1? Is f continuous at -1? No, it's not. Which one of the 3 ways to fail the definition of continuity, remember we talked about 3 different ways you can fail to be continuous, which one of those 3 is going on here?
Removable.
So
Like removable discontinuity.
it's true, the discontinuity is removable. That is true. Remember we said the 3 ways we can fail to be continuous is if the limit doesn't exist, if the function is undefined, or the limit can exist,
Oh,
be defined, but the value of the function doesn't equal the value of the limit. So it's that third one here, right? The limit definitely exists. The function is defined, but the value of the function and the value of the limit are not the same. So it's a good problem. I'm glad you guys asked to look at this one. I think there was one more. We wanted to look at, what did we do earlier? We did 15 first, right? Then 2, so now is 11. Okay, let's take a look at 11. This is another one of these kind of derivative looking limits. I'll start it here, why not? And And this time I will copy it down and then go all the way back to the dot cam so I can use all my space. We want the limit as h goes to 0 of 6 plus h to the negative first power minus 6 to the negative first power all over h. Okay. Who can help me get started here? What would be a good first step on this limit?
Oh, I mean, I'd say just write them down as reciprocals.
Yeah, if I have dog shit raised to the negative first power, that's 1 over dog shit. Anything to the negative first power is 1 over that thing. So quick question, I'll do it up here. Is 6 plus h to the negative 1 minus 6 to the negative 1 over h the same thing as 1 over 6 plus h minus 6 times h? Is that how that works? Can I shove?
Yes, that makes sense. Oh, wait, yeah.
It's tempting, right? It's tempting, but it's not true.
Is it? Wait.
Has the negative power on their own, and they're being subtracted. Remember your order of operations. The power has to be done before the subtraction. So really what we have to do is take the reciprocal of each of these individually and leave those reciprocals upstairs to be subtracted. So this is not true, although it's tempting.
Right.
So this is a common algebra trap. And the safe bet is to try not do too much at once. Remember, just treat each little piece with respect. So each little piece here, who's being raised to the negative first power, I'll treat him as 1 over that thing, and I'll keep it all in context. So this is 1 over 6 plus h minus 1 over 6. And remember, of course, we think about it like this. These fractions are all grouping symbols. So if we're being careful with our parentheses, we could write it this way. But the main thing is that each one of these we treat as a reciprocal on his own, or on her own, on their own. Now from here, it's not too bad. From here, we just need to have a common denominator. When I see big messy things like this, a giant fraction, the fraction or difference of fractions in the numerator, I would prefer to write this divide by h as a multiply by 1 over h. That will save me having to write that big annoying fraction. So this would be what my first step looks like, and then I'll have 1 over 6 plus h minus 1 over 6.
Okay, just a quick question. That is indeed the derivative of 1 over x at 6, right? Just making sure.
Yep.
Okay.
And we'll see what that is soon. So far we haven't talked about those, but yes. Okay. Now I need to have a common denominator between these two pieces in order to put them together, right? Because I'm subtracting two fractions. And the only reasonable choice for a denominator is the product of the denominators, right? A common denominator has to be divisible by each of the two denominators on their own. So this guy I will multiply by 6 over 6. This guy I will multiply by 6 plus h over 6 plus h. So I'll have the limit as h approaches 0 of 1 over h times 1 over 6 plus h times 6 over 6 minus 1 over 6 times 6 plus h over 6 plus h. Is everybody comfortable with that step for getting a common denominator? So when in doubt, just use the product of the two denominators. And of course, remember these fractions, they're grouping symbols. So everything here is in their own little parentheses. So we have to distribute where appropriate. I've still got my 1 over h out front. When I multiply these fractions straight across, I'll get 6 over 6 plus h times 6. And there's no need to distribute that denominator. I would just leave it like that. Minus, here 1 times 6 plus h is 6 plus h. And downstairs I have 6 plus h times 6. Hammy, be good. Okay, and the reason I keep writing these in parentheses, I want to remind myself that this negative is going to get distributed. So I have lim h to 0, 1 over h. This is 6 minus parentheses 6 plus h over 6 plus h times 6. And now I can put this in a single fraction. When I distribute this negative, I'll have 6 minus h upstairs. Downstairs, I have the 6 plus h and the 6. And now I can multiply this fraction straight across. So I have also downstairs h as a multiple, as a factor. Six minus 6 is, of course, 0. So if we come over here to finish things up, have negative h over h times 6 plus h times 6. And now I can cancel the h's because they are factors of the top and bottom shared. The numerator is h times negative 1, so when I cancel that, he just becomes negative 1. And I get limit h to 0, negative 1 divided by 6 plus h times 6. And now that the denominator doesn't have a factor of h, the denominator is no longer 0 when I plug in h equals 0, I can go ahead and plug it in. I get negative 1 over 6 plus 0 times 6, or negative 1 over 36. Not too bad, right? So the algebra is crucial, right? The number one hurdle to getting through calculus and understanding calculus is the algebra. So make sure that your algebra skills are sound. If you're not sure if you can do something, like this little thing at the start here, is this kosher or not? If you're uncertain about a step, rather than guessing or hoping and assuming and continuing, check it. Plug in some numbers, see what works. If you're still not sure, Google it. By all means, Google shit. Ask your friend, ask your buddy, ask your neighbor. Sometimes I ask my dog, but he's not very good at answering those questions. But make a point of verifying, right? We want to train very, very careful thinking in this class. Okay. Are there any other homework problems that you guys would like to look at? Anything else that has been driving us nuts, keeping us awake, causing us headaches? Because if not, I do have something else I would like to talk about. If so, I would prefer to address those.
No, not clear.
Okay. Homework going once, going twice.
Oh yeah, this is not related, but you remember that limit I had, that two-dimensional limit that I asked you about?
Yes.
Turns out it's just one. It was a waste of time.
I think it depends on the path you take, but we can talk about that separately.
I mean, when you take like square root of like 0 minus, I tried looking at it from like a one-dimensional perspective, just like all the different permutations. So like 0 minus to the 0 plus, 0 minus to the 0 minus, and you know what I mean, right?
I do. But I don't
I mean,
extract
and I
products.
looked at a 3D graph, and it still looked like it was going to 1, except when you had like when you were coming from like negative roots, like the square
Yeah,
root of
so
like negative something.
the path dependence there is problematic. And again, that's a good topic for after class, or if you wanted to come to the math team meetings, it'd be a great topic for math team. But for now, we have another section I'd like to discuss. This is on limits at infinity. And this will give us another way to look at the kind of questions we're asking about indeterminate forms. So this is not a terribly difficult section. And it will be on your homework next week, but I want to kind of prime you for it. I want to get you ready for it. It's not the worst thing in the world, but next week we're going to be rushed for time. And it's something that I wanted to include in this week's homework, but it was going to make the homework set too long. So let's introduce limits at infinity and see if we can get a feel for them. I'll give you an intuitive definition. We say that the limit as x goes to infinity of f of x is equal to L, provided the outputs for f of x can be made as close as you want to L by using bigger and bigger inputs. So if you put bigger and bigger and bigger numbers in for x, i.e. you let x go to infinity, the output f of x gets closer and closer and closer to L. Picture here looks like this. Here's the horizontal line, y equals L. Here's the graph, y equals f of x. And as you go further and further and further and further out to the right, the outputs from f of x, those y values, are getting closer and closer and closer and closer to L. And what's more, you can get as close as you want to L by taking x sufficiently large. All right, so this is what it means to say that the limit as x goes to infinity of a function is L. Where have you seen this sort of picture before? Or if I drew this picture for you, how would you describe y equals L in relation to the function f of x?
It's probably like sine multiplied like 1 over x or something.
Oh, let's not get too ahead of ourselves. I'm just thinking in terms of words. So I'm not trying to guess at a function that looks like this. I'm just asking, what terminology have you seen in your algebra classes to describe this type of behavior?
Oh, okay, asymptote, right?
Yeah, it's a horizontal asymptote. And that is a fact. It's not a theorem, it's just a fact, or even a definition. To say f of x has horizontal asymptote y equals L means either the limit as x goes to plus infinity of f of x is equal to L, or the limit as x goes to negative infinity f of x equals L. Now, I haven't explicitly defined what it means to take a limit as you go to negative infinity, but it's the same thing, you just turn the picture over, right? So if as you run off to the right, your y values get closer and closer and closer to L. That means the limit as x goes to plus infinity of f of x equals L. If as you run off to the left, your y values get closer and closer and closer to L, that means that the limit as x goes to negative infinity of f of x is equal to L. And my favorite example of this behavior is a function that I wish I could say everybody knows well. It's a function that everybody should know well, but not everybody does. So I will start maybe here by drawing the graph, and then I'll label some things, and I'll see if anybody recognizes this guy.
That's probably inverse tangent.
Yeah, very good. This is the inverse tangent function. Now he has two different horizontal asymptotes. He has one on the left and one on the right, and they're not the same, which is something that we don't see in rational functions, the other place where you usually encounter horizontal asymptotes. So this guy, y equals inverse tangent of x, he has two horizontal asymptotes. One of them is the line y equals pi over 2, and the other one is the line y equals negative pi over 2. And if I wanted to describe this, so this is an example. If I wanted to describe this in the language of limits, I would say the limit as x goes to infinity of the inverse tangent function, inverse tangent of x. If I go further and further and further and further to the right along this graph, those y values will get as close as you want to pi over 2. So the limit as x goes to plus infinity, right, if I go further and further, these will even get closer and closer. That limit is positive pi over 2. And if I were to go all the way out on the left, further and further and further out this way, my y values are getting closer and closer to negative pi over 2. So the limit as x goes to negative infinity of the inverse tangent of x, that's negative pi over 2. So this is a classic and very important example. Let's look at some more. Now, I'll give you a second to get this in your notes. Right? So make sure you get this example in your notes. If this isn't a graph that you know or recall from your trig classes, I want to implore you to make it something that you know now. Other points on this graph are 1 comma pi over 4, negative 1 comma negative pi over 4. In fact, it's an odd function, so once you know a point over here, you automatically know the symmetric point over here. Of course, 0 comma 0 is there. Square root of 3 comma pi over 3 would be like up here. So this function is a very important function. Inverse trig functions in general are very important, but this one especially is a source of a lot of great examples. So make sure that this inverse tangent function becomes a friend, becomes something that you know well. Okay, some other limits at infinity. Who can help me with this one? The limit as x goes to negative infinity of e to the x. Do you remember what the graph
Okay.
e to the x looks like?
Yep, it goes towards 0.
Yeah, very good. So if you draw this graph, and this is another one of these graphs that we really should know. It's understandable, if forgivable if it's not in our head already, but we want to get it in there and keep it in there. He looks like this. And as we run off to the left there, as I let my x values go further and further towards negative infinity, and all the way out here to the left, my y values get closer and closer and closer to 0. So that's the horizontal asymptote there. This point.
And you can also think about it as like 1 over e to the infinity, which is like 1 over infinity, which is just 0.
Yeah, yeah, that's a valid point. We can bring that up here. So this is the same as if you wanted to write it like that. We've talked about arithmetic and algebra with the infinity symbol. This is e to the negative infinity, which would be like 1 over e to the positive infinity. And if you were to run all the way out to the right, that's definitely 1 over infinity, which would be 0. So we kind of spoiled it. What's the limit? As x goes to plus infinity of e to the x. If I'm on this graph, y equals e to the x, and I wander all the way off to the right, where are my y values going?
Positive infinity.
Yeah, positive infinity. Okay. What other sort of examples should we look at before we start playing with those? There are some things that can go wrong here. What about this guy?
That's the same as the 1 over x as it approaches 0, so we already know.
So the graph of sine x, remember, looks like this. And it just wobbles like this forever. So as I go out further and further and further to the right, are my y values settling down towards any particular value? No, they're not, right? This function just keeps oscillating forever and ever and ever and ever and ever and ever and ever. The y values don't get as close as you want to any particular number as x's get bigger and bigger and bigger. So this, we would say, does not exist. If you wanted to explain, it's because sine oscillates, but never settles down as x goes to infinity. Okay. So having a limit, having a finite limit at infinity or at negative infinity is equivalent to having a horizontal asymptote. Not every function has those, right? Many functions don't. Some, like e to the x, will have an asymptote on one side, but not on the other. Some, like sine, don't have any settling down behavior on either side. There is, however, an important family of functions that we've studied that do have this behavior, and those are like rational functions. What about this guy? The limit as x goes to negative infinity of 1 over x. Again, I'll draw the graph. And this is another graph that we should know. 1 over x on the right-hand side, I know he looks like this. And on the left-hand side, I know he looks like this. I've got a vertical asymptote here at 0, but that doesn't tell me anything about this limit because I'm asking, what about these guys? So if I'm on this graph and I go further and further and further to the left towards negative infinity, are my y values getting closer and closer and closer to something?
Yes.
Yeah. This horizontal asymptote here is y equals 0, right? My y values will get closer and closer and closer to 0 as I wander out to the left, just like they do as I wander out to the right. I get closer and closer and closer to 0 on both sides. So this, I would say, is, you could write it as 1 over negative infinity. And if you think 1 over infinity is 0, well, then 1 over negative infinity, that has to be 0 also. You can call it negative 0 if you want, but negative 0 is the same as 0. So we're to a place now where I can start talking about rational functions in a little more generality. Perhaps I'll do one more example before we get there. Any questions on any of the examples on this page here? So these are kind of foundational problems, foundation examples. We need to be comfy with these, including the arctan one, the inverse tangent one. So zoom out a little bit more. Any questions on any of these? All comfy cozy? Okay. So let me do one more example with a rational function, and then I'll develop a little theorem, and that's where I'll leave you guys for today. So there's a trick for calculating limits at infinity for rational functions. Remember, rational function means ratio of polynomials. So let me call this guy 4x cubed plus 2x squared minus 3x plus 5 over 2x cubed minus 7x plus 4. I'll tell you right now, I don't have a goddamn clue what this graph looks like. Just made this thing up. But I want to find what happens as x goes to infinity. And there's a trick here that I'm going to use. And you could, I would regard this thing as a theorem, or maybe a lemma. It's a name for a little theorem. If p is positive, then the limit as x goes to infinity of 1 over x to the p will be, well, it's going to be 1 over infinity to the p, which is infinity, which is 0. So we're going to use this theorem. Now, what I don't see anywhere in here is something that looks like 1 over x to the p. So there's a trick to making that sort of stuff show up in rational functions. I call it renormalization, which is a word I steal from physics, where we divide top and bottom by the largest power of x occurring anywhere. So the largest power of x I see anywhere here is x to the 3. So I'm going to divide top and bottom by x cubed. I call this the renormalization trick. If I do that, I will see that my limit is equal to, well, let's just write it out. So this will be 4x cubed plus 2x squared minus 3x plus 5. I want to divide that by x cubed, so I'll multiply by 1 over x cubed. And then downstairs I'll do the same. I have my 2x cubed minus 7x plus 4 divided by x cubed, so multiply by 1 over x cubed. And then I distribute. So I'll distribute this guy to this guy, to this guy, to this guy, and to this guy. 4x cubed times 1 over x cubed is 4. 2x squared times 1 over x cubed is 2 times 1 over x minus 3 times x times 1 over x cubed, that's 1 over x squared. And then 5 times 1 over x cubed is just 5 times 1 over x cubed. So that's my numerator. And down here I do the same thing. I distribute the 1 over x cubed to all of these pieces. 1 over x cubed times 2x cubed, that's 2. Minus 7 times x times 1 over x cubed, that's 1 over x squared. Plus 4 times 1 over x cubed is just 4 times 1 over x cubed. So here is my renormalized function. Now we know our rules for limits. I can give the limit to the top and the bottom separately. And then once I give the limit to the top, I can take the limit of this, the limit of this, the limit of this, and the limit of this separately and add them up. But look at this theorem. It says for any positive number p, 1 over x to the p will go to 0 as x goes to infinity. So what is this piece going to go to as x goes to infinity?
0.
This guy?
0.
Yeah, all those guys. So this is 4 plus 2 times 0 minus 3 times 0 plus 5 times 0 over 2 minus 7 times 0 plus 4 times 0. This renormalization trick saves me because at the start, the top looks like it's going to infinity, right? Infinity cubed is definitely infinity. The bottom looks like it's going to infinity. So at a glance, this thing looks like it's infinity over infinity. How the hell do I wrap my head around that? I know it's not 1. We know that. We know infinity over infinity is an indeterminate form. And in this case, infinity over infinity looks like 4 over 2, or 2. And this is how you prove the rule that you guys learned in college algebra about horizontal asymptotes for rational functions. Remember that rule, if the degree of the top is smaller than the degree of the bottom, blah, blah, blah. That rule is proved by this trick. If the degree of the top and the bottom are the same, then when you renormalize, all the other terms will go to 0, and you'll just be left with the ratio of lead coefficients. If the degree of the top is smaller than the degree of the bottom, let's look at one of those. So first questions on the algebra, any of the particular steps here. We'll make sure we're comfy with what we did here. Pretty comfy? So maybe I'll hold off on proving that result from college algebra because we are out of time now. This has sort of been a nice introduction to section 2.6. Remember, we don't have class next Monday because of the holiday. You do have homework, so please try to finish up that homework. And then next Wednesday when we meet, we're going to wrap up section 2.6 and then start talking about derivatives. So next week, rates of change, the derivative as a function. We may end up having to move some of this because next week is a short week and we still have to finish up this. But next week, we will start talking about derivatives in earnest. And that will get us into the meat of Calc 1. So I hope everybody has a lovely weekend. Please do finish up that homework. Read section 2.6 in the textbook. It is worth your time to read the book always. 2.6 is not a hard read, but there's a good amount of stuff in here that deserves your attention. And I think they probably go through that proof. Yeah, here's the theorem we used. Maybe not. But then there are a few other extra tricks. So we're going to learn some extra sneaky tricks for limits at infinity. And then we'll start talking about derivatives. So that is it. I hope you guys have a lovely weekend. If you're stuck on anything in the homework, don't hesitate to ask for help. If you've been waiting for a response to a WebAssign question, I will get to it right now. And if you want to come see me in office hours, of course, you can always do that, or you can send me a Canvas message for help on any particular problems. All right, I hope you guys have a lovely weekend. Enjoy the holiday. Take care of yourselves, and I'll see you on Wednesday.
Thank you. See you.